And good afternoon. My name is Rohit. I am currently working as the AI scientist at Course 5 AI Labs. And today I'll be, so just to talk about Course 5 AI Labs. So Course 5 AI Labs is a R&D unit of Course 5 Intelligence based out of Bangalore and India. So today I'll be presenting on domain adapted abstractive summarization of dialogue using transfer learning. So you can expect this topic basically around abstractive summarization of dialogues. So let's get started. So recently, what we find is that abstractive dialogue summarization task is getting a lot of attention in terms of its industrial application. So one application you can think of is online meeting, where just like this meeting, where you would like to basically summarize the key insight of that meeting as the meeting ends. And we also know that due to the recent advancement in the field of transfer learning, especially due to the availability of the transformer based language model, it has pushed benchmark in many tasks of NLP. So leveraging these pre-trained language model and adapt it to the dialogue scenario can help a lot. If you look at the earlier research, what we find is that mostly it's around abstractive summarization of you can say documents or articles. But if you compare a document article with a dialogue is very different, right? So if because a dialogue consists of has this hierarchical structure where you have multiple speakers, and each speaker has this different way of you can say speaking, and as the conversation progress, you can expect there is a change in the topic. So we can't just treat dialogue as a document and then build a solution. So we need to adapt to the dialogue scenario, which is very important. uh, so what we find is that very little research has been paid on adapting these pre-trained language model to the dialogue scenario. And to solve this problem, of abstractive dialogue summarization, we propose a simple yet effective hybrid approach, which basically consists of two modules. So I'll just move to the next slide. So before I go through the process flow of this hybrid approach, I just quickly wanted your attention on figure 2. So in the figure 2, you can see that it's represent an example from AMI dataset. So you can see that we have a raw transcript which contains basically 200 plus terms. So this in a way is a very long transcript, you can say. And for every utterance, you can see that we have a corresponding speaker type or speaker role. So basically PM here you can see is like product manager, ME is marketing expert. So and they have like a different style of you can say speaking. And also for every utterance we have a corresponding label, whether that utterance is important or not. And we also have a human labeled abstractive summary for this transcript. So imagine a case, right? You wanted to solve this problem, you wanted to write abstractive summary of the conversation, right? So the way as a human you would do it is in two steps. The step one would be you highlight the important utterances from multiple speaker, and then you sort of rephrase that to create a abstractive summary, right? So in the similar way, we present this hybrid approach. So in the figure 1, you can see that given a long dialogue transcript, we apply module 1 and module 2 as a part of our hybrid approach. So in the module 1, depending on whether we have the utterance level labels or not. So utterance level labels like this 1 or 0, which represent important and unimportant. So we can use supervised or unsupervised. So under unsupervised, we compare basically two methods. One is very old text rank, and another one is utterance cluster rank. And under supervised, we present a hierarchical model, which we call hierarchical BERT highlighter or HBH. So the goal of the module 1 is just to highlight the important utterances, right? So once we have the important utterances, then we apply the module 2, where we adapt transformer based into encoder-decoder model, and finally generate and train it like as a sequence to sequence task, and generate a final abstractive summary. So now I'll dig deep into each of these model which I just talked about. So like I said, in module one, right? So we have we call this important utterance highlighter. So the goal of module one is, like I said, it highlights the important utterances, right? So if we let's say if we start with the unsupervised method, right? So we compare two. If we start with the unsupervised approach, we compare two methods. One is text rank, another one is utterance cluster rank. So if you look at the figure 3, that represent text rank method, where so text rank, as usual, you must be aware that it is inspired from page rank algorithm. So given a dialogue, you split into you can say utterances. Then once you get all the utterances, you get sort of representation of each utterance. So this representation can be a simple bag of words kind of representation. Then from there we create a similarity matrix, which where each value represent a similarity score from ith utterance to a jth utterance, and then we convert it into a graph where each node represents a utterance and edge represents a similarity score, and then we just apply page rank algorithm to finally rank the important utterances. In the similar way, we have utterance cluster rank, but where once we get the utterances, we represent them by using a pre-trained BERT model. So more specifically, we use BERT small. So the whole idea is that the BERT that it would give you a deep contextualized representation of that captures the context of each utterance, and then we just apply a clustering algorithm to create k clusters, and you can think of each of these k cluster represents some topic, right? And we, from every cluster, we pick the utterances which are more close to the centroid, and that becomes the important utterances. So this was the unsupervised approach. Now imagine if we have those utterance level labels, right, where one is important, zero is unimportant. Then we present what we called a hierarchical BERT highlighter, which is actually a hierarchical model. This is how the architecture of hierarchical BERT highlighter looks like. As you can see, it basically consists of two components. One is token level BERT encoder, and another one is utterance level BERT encoder. For initialization, again, we use BERT small only. Um, so given m utterances from the dialog, the first step is the token level BERT encoder, which gives you the representation of each utterance from the CLS token. So once we have I mean utterance of once we have a representation corresponding to the CLS token for all the m utterances, then it goes as an input to the second component, which is utterance level BERT encoder. So this utterance level BERT encoder tries to capture the utterance structure, tries to learn that utterance structure by applying the multi-headed self-attention. And then finally, we get the output logics, which we compare with the labels by calculating the CRF loss. So just to mention one point, that the reason why we are using CRF loss, because as you know that in CRF you create this transition matrix, right, and you try to maximize that path. So what CRF would do is that when it is predicting a jth utterance, whether it is important or not, it can take into account whether the left I mean utterance on the left or right are important or not. So once we so the goal of the module one was be it supervised or unsupervised, we end up with the important utterances. Once we have the important highlighted utterances, next step is sort of rephrase them to in an abstractive manner. So for this we actually adapt a pre-trained encoder-decoder model and fine tune as a sequence to sequence task to generate the final abstractive summary. We basically compare T5, BART, and PEGASUS and adapt it to the dialog scenario. More specifically, we compare T5 small, BART base, and PEGASUS distill. So you can see that all of them are actually 6-layer model, right? So before I, move into how we are adapting these, these three pre-trained language model, I just wanted to quickly go through, how the pre-training, what kind of pre-training objective is basically used in these models. So this give you idea that, like why we basically specifically choose these three model for comparison. So starting with the T5 for figures, you can see that the way they perform the pre-training is that given a original text like quick brown fox jumped off the lazy dog. So what they do is basically they mask a span of text and then replace it with the sentinel token. So X and Y you can see is a sentinel token. And then the goal of the decoder is to basically predict that sentinel token. So, and you just train it end to end. So you can think of this pre-training objective is similar to closed task basically. Now moving to the figure 7 where we have BART. So BART is actually auto denoising network where they corrupt the text by applying different noisy function to the input text. So for example, if you see this green bar, it represents you can think of this as basically two sentences where ABC tokens are from sentence 1 and DE from sentence 2, and then you apply different corruption to noisy function to corrupt the text, like token masking, which is very similar to the way we do in BERT. Then sentence permutation, document rotation, token deletion, text infilling, where you just mask a span of text. And then this is what goes as an input to the BERT encoder. Then the decoder is trained in a auto-regressive manner, the way we train GPT-1 and GPT-2. Then we have Pegasus. So in Pegasus, basically they use two objective function, two pre-training objectives. One is mask language model, and another one is GSG, which we call gap sentence generation. So for MLM, it's very similar to the way we do in BERT. So you randomly mask some of the words, and then the goal of the encoder is to basically predict those words. As you can see, mythical and names is replaced with mask2, and then goal of the encoder is to predict these two words. And for gap sentence generation pre-training objective, we mask the whole sentence in that text, and the goal of the decoder is to generate that whole text. So if you compare all these three models, right? So I mean, I can say that gap sentence generation is very this pre-training objective is very similar to the fine-tuning objective that we use in while fine-tuning for abstractive summarization task. So you can imagine that Pegasus in general requires less data compared to these two models. But it also depend on the domain on which it is basically trained. Now in this slide, we represent the module 2 by adapting those encoder-decoder model, which I just talked about. So given the important utterances from the module 1, idea is that the way we adapt to the dialogue scenario is that if you look at the input, each important utterance is separated by a special token called end of turn. And then in order to help then we have the token embedding corresponding to each token, and then we add speaker type or role embedding. The idea of adding this is it would help the model to distinguish between which utterances from which speaker. For example, here you can see in the example that uh, basically if there are 4 utterances u1, u2, u3 and u4, and u1, u2 belong to speaker 1, and u2 and u4 belong to speaker 2, and then this is how we add the segment embedding corresponding to the speaker, and that's what goes as an input to the encoder. And decoder is as usual trained in a teacher forcing manner, where at each time step you get the probability distribution across your vocabulary, and then you compare it with the gold label to calculate the cross entropy loss. So in general, what we are doing is trying to maximize this condition probability function. So now that you have understanding of model 1 and model 2, and we did some benchmark on publicly available data set. So in general we use this 4 data set. You can see that all of them are from different scenario, like online, daily life, or meeting. And the one thing to note down here is that if you look at the AMI data set and ICSI data set, you can see that the data size is very low, right? 137 and 100. So and another thing is that in these two data set, the transcript is very long. So you can imagine like 2000 plus words are there, as compared to other data sets like Samsung and Dialog Sum. For evaluation, we consider standard ROG metric. More specifically, we compare ROG1, ROG2, and ROG-L. I won't go into the detail of this metric, but you can see here that if we have a reference and we have a model prediction, so in ROG1, we actually compare the unigrams, and in ROG2, we compare the bigrams, and in ROG-L, you compare the longest common subsequence. And for every case, we actually calculate the F1 score, and that's what we use for comparison with the other baselines which are available. Then finally, we have the results. So as you can see that we have the hybrid approach, where depending upon the combination of different combination of model 1 and model 2, like supervised, unsupervised, and model 1, model 2, we have these different hybrid models. The best result I have marked in bold. So we have compared it with the 4 baselines. So starting with the first baseline, which is transformer non-pretrained. So as you can see that there is a significant difference, you can see, so which shows that how pre-training can be helpful, and just doing the direct fine tuning can reduce the performance to a great extent, and especially when you are dealing with the lower source data, like in case of AMI and ICSI. Second baseline is actually a very good baseline for extractive summarization. Here also you can see that for all the cases, hybrid approach is like better, which shows that human mostly prefer abstractive summary compared to extractive summary. Then we have PGNet, which is a pointer generator network. It's very old, you can say, architecture, and it's actually a good architecture for you can say document summarization. And here also we can see that there is a significant difference, that hybrid is better, which shows that it's very important to carefully adapt your models, pre-trained language model to the dialogue scenario instead of treating it as a simple document. And then we have HMNet, which we call actually strong baseline. And this is a very recent model. It's actually an end-to-end hierarchical model for meeting summarization. If we compare our results with the HMNet, we can see that mostly it's basically comparable. If you look at the basically the ROG1, ROG2 scores. But one thing to note down is that in case of HMNet, they basically propose a pre-training strategy. But in our case, what we are trying to do is that we just leveraging whatever is already available, and just we do fine tuning, right? And fine tuning is less resource intensive as compared to pre-training. Overall, what we find is that in case of module 2, BART base is better compared to other two. And in case of module 1, if we can see that if we compare, let's say, these two are the first two are unsupervised approach, and this one is a supervised approach for module 1. So HPH, that supervised approach is better compared to unsupervised approach. And under unsupervised, we can see that utterance cluster rank is better compared to text rank, or it's slightly better, I would say. At last, I just wanted to conclude that what we have presented is a simple hybrid approach, which allows you to adapt the pre-trained language model to the dialogue scenario, especially when we have a very long transcript. Since we are using pre-trained language model, so we can use it in low resource setting for domain adaptation. Here, low resource not just mean in terms of data, but in terms of compute power also, because we just do fine tuning. And based on the experiment results, we can say that we are able to achieve state of the art results. And with this, I end my presentation. Thank you very much.